All right, guys, we're starting chapter 9. We're going to do some experiments. Okay. Now, chapter 9 is all about momentum. And momentum is a pretty simple formula, and it sort of encapsulates Newton's first law in a way. The equation is m times v. That equals p, or momentum. We call momentum p, not m because m is mass. So if you take an object's mass and multiply it by its velocity, that is the quantity called momentum. Now, momentum is what we call something that's conserved. It's a conserved quantity, meaning that if a system is left alone, its momentum can't change. Okay. Now, if the system consists of two particles, okay, if they collide, the momentum before and after the collision is the same. Right? Momentum has to be conserved. The only way it can change is if an outside force acts on it and maybe takes momentum out of the system. Okay, so now I'm going to use my force sensor again. Okay, and we're going to do some experiments here. Okay, because one of the things about momentum is it also can tell us how much force there's going to be in in the case of, say, a collision. Okay. If you've ever been in a car accident, then um you've experienced a change in momentum. If you look at a modern car, the inside of the car is squishy, right? There's foam padding everywhere on the inside of the car. Okay. Now, older cars, let's take a look here. Okay. So, metal interior of older car. Oh, let's look at this. Okay. Let's do 1945. Yeah, 1945. Okay. Let's look at, ah, here's a great picture. Vintage car from the 1950s and 60s. Sure, let's visit that site. Hopefully it's nothing weird. Okay, so no, I wanna see the inside of the car. Okay. Really? Nope. Mm. Ah, let's look at this one. Beautiful. Okay, so this classic car, right? It's got an actual, it looks like metal dashboard. Okay, so it is solid steel, I guess. And also look at the steering wheel. It's actually made out of wood. Everything on the interior is actually metal. Okay. Now, if you compare that to the interior of a modern car, all right, um, let's compare this one. So the interior of this car, there's a squishy dashboard. The foam is some kind of plastic, but there's airbags everywhere. It looks like a lot of the dashboard is either plastic or it's covered with something a little bit squishy. Okay. Now, the purpose of that foam is to provide more cushioning if your head were to hit the impact, or your head were to impact it. Okay. Now, the way that it works is if there's a change in momentum, then that is equivalent to experiencing a force. And the faster your momentum changes, the higher that force is going to be. So if you suddenly stop, okay, you're going to experience a much higher force than if you came to um, came to a rest gradually, which makes sense, right? If you lean back, you definitely want a pillow there to slow you down because that's going to lessen the force. But the way that it does that is it basically increases the time of impact, okay? And when that happens, it lowers the force. Okay, we're going to talk about this. It's force and impulse and the change in momentum. Okay, the change in momentum is we call that impulse. Okay, but let's look, and I'm going to show you the equations in a minute, but let's look at an example here. Okay, so I'm going to take my little physics cart here. Okay, and if you could see, I'll show you my part of my office. Okay, so my office desk is it has been converted into yes, my desk has been converted into a miniature physics lab because of this course, which of course is amazing. I love that. Okay, so here is my here's my desk. Okay, so I've got this cardboard here, and then I'm gonna make a ramp here. All right, so you're gonna get a bird's eye view here. Okay, so here is my desk, and see, I've got this little cart right here, and I've got my yeah. See, it's gonna go right there, and then it's gonna go into this hard shelf right over there. Okay, so and at the end of here, I'm going to attach a force sensor right here. Okay. Well, this is just a metal plate. Yes. I'm going to put on this little metal plate here. I got a screwdriver. I'm just going to tighten that out. Let's see. Now, I love doing physics experiments and I love making all these little experiments that I do for you guys. I hope you like them too. Okay. All right. So we got this metal plate here, right? It's just a piece of metal, okay? And all right, let me shine some light right over there. Alrighty. So the cart's gonna go right down here, and then we're gonna record some force data here. So I gotta save my calibration. Haha. All right, did we get it here? Here's my cart. Okay. And okay, so when I press on it, so we're gonna go right down the side here. Put it down here on the wheels. Here we go. No, my cart. Ah. Okay. Well, sometimes experiments don't always work. Oh, jeez. All right, let's see what do we get here. Oh, should we? Oh, shoot. Okay, so that was the force. Okay, so look at that. I got 13.4 newtons. Okay. So cool. All right, we're gonna save this data here. Okay, 13.4 newtons. And my acceleration, yeah, I had some good acceleration there. And then my position changed and my wheel velocity. Okay, so yeah, we got I'm gonna all right, let's see. Oh, you know what? I'm gonna zoom in on this data here. All right, look at this. My velocity versus time graph. Wow. That is, oh man, this is amazing. Okay, let's take a look at that. Look at this. Look at right here. Oh, here's the webcam that was this is my remote camera here. Oh, gonna move that guy out of the way. Got a lot of cameras in here. All right. So look at this, guys. It's a perfectly linear thing until right there. Okay. And that's where the collision happened. Okay. So here's my position. This is the position of our, and look at this. Oh. It's beautiful. It's the rate of change here is it's linear. That is amazing. It's accelerating. Our velocity is changing, so we get a constant acceleration. Right? And then right here, this is our collision. I think. I don't know what this first one is. I guess that was the collision. This must have been when it bounced. Yeah, that was after a bounce. Okay. All right. Well, anyways, we're gonna save this data, and then we're gonna get a new acquisition set. We'll get the same thing here. We're gonna do force, wheel acceleration. Oh, why didn't we do wheel acceleration? Wheel position and wheel velocity. Okay. Wonderful. So we're gonna do that, but first. Okay, we're gonna make something for the end of this. All right, so let's go to my workshop. Dr. Wisby's desktop workshop. Okay. So we're gonna use this camera now so you can see what I'm doing here. Okay. So we're basically get my little webcam here. Okay. All right, so here is this thing. Now I'm gonna put something on the end here. Okay. Basically, I'm gonna put some this is just some paper. Okay. So I'm gonna attach the screw here to the paper instead. Okay. So how can we put that on there? Oh, I got some scotch tape. Yeah. We'll put some scotch tape on there. That should do it, man. Okay, so I'm gonna get a piece of tape here. Okay, we're gonna put one end over here. Now, in retrospect, I should have made each of you rent this little sensor so you could hook it up to your computer. But would have, should have, could have. Oh well. That would have been another $80 or something. So I didn't know if you wanted to do that or not. But all right, we gotta attach this somehow. Okay. All right, we're gonna make it a little. Now this thing drags on the ground. We don't want it to slow it down. Okay, well, you know what? Just need to hold this thing on here. Okay. So, all right. So we'll put this guy here. Now, I don't know about you, but I love making physics experiments. Okay. I love building things and I love doing things with my hands. And to me, physics is all about doing experiments. Because in my lab, I work with quantum information. And so I'm trying to find the right material to build a quantum computer out of. And so I do a lot of experiments. That's what my research is funded for, is to do experiments. And so that's kind of my whole thing is experimental physics. All right, so we got this big squishy pad here. Okay. Now this is pretty squishy, right? I'm hoping it's kind of squishy here. Okay, we got this paper here. Maybe I wadded it up too much. Okay, but we'll do this as a first attempt. All right. Yeah, we'll check it out. Hmm. I didn't think about how I was gonna tighten it though. All right. Well, screw this in here. All righty. We got our center here, and it is ready to go. Okay, we're gonna try and set this thing up the same way. Shoot, I don't know. Right, then we're gonna go over here. Here we go. Oh, we got to get the force sensor going. And what do we want here? Uh, of wait, wheel velocity, wheel position, wheel acceleration, and the force. Yeah, okay, here we go. Validate your configuration. Okay. This thing shut off. Yep, it shut off. All right, we're gonna turn this back on. All right, here we go. I'm gonna put our sensor up here and I'm gonna hit ah run. Shoot. I'm gonna put this roughly where it was. Okay, let's pause our measurement here. Let's see what we got. Okay. So my force here, this was, let's zoom in on this. We're gonna see if we can detect anything here. Okay, so this first peak, that was our initial collision. Okay, so we've got this. That was our first peak. Let's go to page one. And I'm a little confused. We might need to repeat some of our data. I'm a little confused here because honestly, this doesn't not make sense. Hmm, okay. Hello there. We are going to do another problem, and we're going to introduce a new concept called impulse. Impulse roughly is equal to the change in momentum. Okay, now that's really important because the bigger the change in momentum is, the higher the force that you're going to experience. Okay. And it also depends on how quickly the momentum changes. Okay. This is why we have airbags in cars because the airbag increases the time of the collision and that reduces the total force that you experience inside of a collision in your car. And we're going to do some experiments and we're going to do this problem. But let's start with this problem first of all and we will use it to explore impulse and how momentum changes. All right, now this is a great problem because there's a falcon, and who doesn't like falcons? I love falcons. All right, so peregrine falcons frequently grab prey birds from the air. Okay, sometimes they strike at a high enough speed that the force of the impact disables the prey bird. A 480-gram peregrine falcon high in the sky spies a 240-gram pigeon at some distance below. The falcon slows to a near stop, then goes into a dive called a stoop and picks up speed as she falls. The falcon reaches a vertical speed of 45 meters per second or about 95 miles per hour. That is, wow, that's fast. Which we can assume is, and she strikes the pigeon at 45 meters per second or about 95 miles an hour. So this pigeon is up above the falcon. It goes straight down into a dive and hits the pigeon at 95 miles an hour. I mean, that probably kills it, I'm guessing, or disables it, knocks it unconscious. Okay. The falcon strikes the pigeon and grabs it in her talons. The collision between the bird lasts for 0.015 seconds. Okay, so we're gonna start, of course, by writing down everything that we need in the problem. Okay, so this is step one, and I've been messing up a lot on this. I don't read the problem carefully. Okay, so definitely read the problem carefully and then take notes of everything in the problem. Okay, this is the first step because this is often where I go wrong. I don't write something down correctly. Okay, so mass of the falcon MF is 0.48 kilograms. And I'm just gonna put it in kilograms right away. I don't even want to mess with grams. All right, the mass of the pigeon is gonna be 0.240 kilograms. I just converted it from grams into kilograms because I don't even want to know. All right, so the initial velocity of the initial velocity um of the pigeon is zero. It's stationary, right? The pigeon isn't moving. Okay, it says that. Yeah. The falcon slows to near stop, then goes into dive. The falcon reaches the bird, which we can assume is stationary. Okay, so the pigeon is stationary. When the falcon, okay, we're gonna call this FA, falcon, FAL. Okay, that's my initial falcon velocity. Okay, and my initial PI. Okay, this is my initial falcon velocity. That is going to be 45 meters per second. Okay, and what do we have? The collision between the birds lasts for 0.15 seconds. Okay, that's important. Okay, because we're dealing with it's called an inelastic collision. So when two things collide and they stick together. Okay. So we wrote down all of our information. Oh, and let's draw a picture so we know what's going on. Okay. So here's my falcon. Okay. And its wings are back like this, and it's going into a dive here. And it's gonna be yeah, here's my falcon. I don't know. Does it look like a falcon? I don't know. All right, close enough. It doesn't have to look like a falcon. Hey, and the falcon is going straight down, and here is my nice, peaceful pigeon having a wonderful day in the park. It's flying around. Maybe it eats some seeds. Just here's my pigeon. Oh, okay. There is my pigeon, and I really like drawing pigeons actually. If you've ever seen the TV show Portlandia, there's this episode called Put a Bird on It, and they basically put birds that look very similar to this on everything, like pigeons, okay? And so our pigeon is having a wonderful afternoon in the park right before it is instantly killed by the falcon. Oof, ouch. Nature is kind of mean sometimes, but I mean, the falcon's got to eat. All right, so our falcon here is headed straight down in the Y direction. Okay, it's going downwards. We're going to call that down. So we're going to say that this is minus 45 meters per second because it's traveling downwards. Okay, so this is everything that we have. We'll label this falcon and pigeon. All right, what do we need to know? What do we need to find in our problem? Aha! What is the final speed of the falcon and the pigeon? Aha, okay. Well, so once these two things collide, right? The basically the well wait, I'm confused. All right. What is the final speed of the falcon and the pigeon? Express your answers in appropriate units. Let's look at the problem here. I'll share my screen with you and we'll read the problem because the question is, do the pigeon and the falcon stick together? Okay, the falcon reaches a vertical speed of 45 meters per second before striking the pigeon, which we can assume is stationary. The falcon strikes the pigeon and grabs it in her talons. Yes, the falcon grabs it. The collision between the birds lasts for 0.15 seconds. Okay, so they're stuck together. That's what I'm going with. Okay. All right, so what we do know about this problem, okay, is that, and this is the most important thing about these momentum problems, okay? Momentum is conserved. That means the momentum of the two things is the same before the collision and after the collision, okay? Momentum before the collision equals momentum after the collision, okay? So, Initially, what is the momentum in the problem? Well, the only thing that's moving is the falcon. Okay. And so all of the momentum, because if you have zero velocity, you have zero momentum. You're not moving. Your momentum is zero. Um, so all of the momentum in the problem is initially with the falcon. Okay, so let's write that down. So initially, our momentum, we'll write this down. Okay, initially, so initially, okay, Falcon has all of the momentum, right? Because our pigeon's not moving. It's in the problem is stationary. Okay, so I'm gonna write this down. So our initial momentum is gonna be mass of the Falcon times the velocity of the Falcon. Okay, that's it. Okay, so we can find that's its initial momentum. Right? It's the only thing that's moving. Now, after they collide, they stick together. Okay? The falcon is clutching the pigeon together. And so after the collision, then these two particles stick together and the momentum is the same. But the thing that has changed is the mass. Okay? So and they're stuck together. So our final momentum. So final momentum. The final momentum of our system then is PF, that's final momentum, okay? And we're going to have a new mass for our system now, so it's going to be mass of the Falcon plus mass of the Pigeon, okay? And then um, our we multiply that times the final velocity of Falcon and Pigeon, okay? Now, we know that our initial momentum equals our final momentum. Okay, so let's write this down here. Momentum is conserved. Momentum is conserved. Okay, right? So this has to be true. All right, so I'm gonna this is what this expression is telling us, right? The momentum of the system before initially, that's our Falcon momentum, has to equal the final momentum of the Falcon plus the Pigeon. All right, so we can just plug everything in here. I'm not going to put any numbers in yet because you don't want to put any numbers in until the end. Just trust me. All right. I think I say that in like every video, but just trust me, it's for real. All right, mass of the Falcon. So I'm gonna put in for PI here times velocity of Falcon. Okay, and this is gonna equal, yeah, mass of the Falcon plus mass of the Pigeon times the final velocity, which is Falcon plus Pigeon. All right, so we want to get this on one side. Okay. So I'm going to divide both sides here. I'm going to divide both sides by mass of the Falcon plus mass of the Pigeon. Okay. And so this is going to be mass of the Falcon plus mass of the Pigeon. Okay. All right. So on this side, this is going to cancel. That's going to cancel. All right. Now, I'm going to get everything in its final form. I'm gonna switch my equations. You can always just write this side first, okay? You have that right. Okay, so now I'm down here. We have mass or velocity of Falcon and Pigeon. It sounds like a cartoon, doesn't it? Falcon and Pigeon. Like some weird cartoon on the internet. Okay. Equals mass of Falcon times velocity of Falcon. Okay, that's our initial momentum divided by mass of Falcon plus mass of Pigeon. Okay. And I can tell this is going to be slower because our denominator is going to get bigger. And so our final velocity of the two things together is going to be smaller, which you would expect. Okay. So if a big thing hits a little thing, right there, the velocity slows down. It has to. and the momentum is conserved. So let's put in our numbers here. Okay, so we got mass of Falcon is how much does our Falcon weigh? How much do you weigh? Which no, not weigh. That's a force. We want the mass of the Falcon. Okay. So we're gonna have 0.480 kilograms times the velocity of our Falcon, which we wrote down that was minus 45 meters per second. And I'm keeping that minus sign in there because in these problems, the minus sign is going to tell you what direction your system is moving. And if you do everything correctly, that minus sign will come out correctly, and so you know what direction your system is moving. Okay. So then in the denominator, we'll have mass of Falcon, which I want to write in the actual numbers now. So it's 0.480 kilograms plus 0.240 kilograms. Okay. And that's going to equal our final velocity of Falcon plus Pigeon. Falcon and Pigeon. Maybe. Okay. All right. So we got that in there, and now I'm gonna throw it into MATLAB. I don't know why I'm always throwing things in MATLAB, but it's fine. Okay. So now my last equation here, I entered the numbers wrong. I forgot that factor of two. I'm not gonna mess up this time, guys. Okay. So it's gonna be 0.480 times negative 45. Okay. Now, I'm looking at the numbers here. I'm not going to forget any factors of two or anything divided by 0.480 plus 0.240. See, and if you solve the equation like this symbolically, okay, then you just type it into your calculator over here, exactly like this. And so you're only going to have to use your calculator once, okay? Use it once and you're done. All right, so the final velocity of our Falcon and Pigeon system is um 30.0 meters per second, and I've got a negative sign, and so that means that it's going downwards. Okay. All right. Okay, so and one thing is I know that this final velocity of these two things should be smaller than our initial velocity. Okay. Because our mass increased. And if your mass increases, okay, momentum is conserved, and so that means your velocity has to change. Okay, so initially, my velocity of the Falcon was minus 45 meters per second. That's a higher velocity. Okay, my final velocity is minus 30 meters per second. All right, so that does make sense. Okay, so if two objects stick together, and momentum is conserved, meaning nothing outside of the system acts on it, okay? Then it your final velocity should be smaller. All right. So we did part A. Let's plug in our answer here. Okay. Now, the reason I do this is because, one thing I want you to know how to do this, and Um, I think it's okay to do this because these assignments take a while, and I made them. I know they're a little bit long, but I know that I want to do some of the problems with you. So hopefully this helps. All right, so we're going to submit our answer. What? Okay, we somehow we went astray. Well, okay. The answer is that this is a magnitude, not a vector, and so they don't want the negative sign there. Okay, so yes, if we're in vector format, it should be negative, but they just want the magnitude. So don't put in that. Okay, so I found the vector. That's the direction. So I should have a y hat here also. Okay, but the magnitude is 30. That's the magnitude of the velocity. That's fine. All right. Part B. What is the average force on the pigeon during the impact? Okay, so what is the average force? And so now we're getting into We're getting into the good stuff now. Okay, so now we need to start talking about something called impulse. Okay, and so let me throw up an equation. All right, well, sadly, the PowerPoint uh, presentation for this chapter, basically all the equations are totally messed up. So, I think what you should do is take a look at the book. The book's actually really good, okay? So go to page 281 in your book. This is chapter 9, part 2, okay? And it's the momentum and the impulse theorem. So momentum and the impulse theorem, okay? And you can read through this, and I think it really explains it pretty well, okay? So I'm going to go through this basically here on paper, and we're going to talk about it and what it means, okay? So, this is page 281 in the book. That's the best explanation. And honestly, the PowerPoint equation, I don't know what happened, but they did something, and it's pretty messed up. So, anyways, we are going to start here, okay? And we're going to say Newton's second law says that the average force is equal to mass times the average acceleration. Okay? This is true. We saw this before, and okay, and what this means is that during a certain time period, right, the average force is what did that force look like? Okay, what was its average value? Okay, and so let's draw a little picture here now. Okay, and let's say during a collision. Right, let me let me simulate a collision. Pikachu has volunteered to demonstrate impulse. Are you ready, Pikachu? I think that means I think that means yes. Are you ready? Let's go. Oh. Hey, guess what? Hey, Pika, should we repeat the experiment to collect more data? All right. Oh shoot. Oh, okay. Uh, don't worry. No Pokemon were actually harmed during this video. Are you okay, Pikachu? Oh, thanks, Pikachu. I'm sorry about that, Pikachu, but okay. So, during the collision, Pikachu experienced some force with the wall, right? And how much was that force? Well, we could put a force sensor in Pikachu. However, I don't want to throw my sensor at the wall that hard because it would probably break. So let's watch this video and collect some data. Okay, so as you saw in that video, during a collision, okay, we're just talking about during that collision when Pikachu was in contact with the wall, right? So imagine Pikachu is flying at the wall. Here's Pikachu. He's got those weird kind of pointy like donkey ears. I don't know. I don't totally understand his ears, but whatever. Okay, the Pikachu is not the point, okay? So as Pikachu is flying towards the wall, let's give him his tail here. Yeah, there we go. Okay. We know that it's Pikachu because he's got that weird tail and he's got those like kind of like stubs for legs, whatever. Okay. So as he is flying towards the wall, here's the wall. Whoosh! He's going right at it. Okay. So Pikachu collides with the wall, right? And we need to put the little red things, his cheeks, because he's got those little, those red spots. Okay, so Pikachu's yellow. Okay, Pikachu's yellow. All right, so we'll just get a highlight, so just enough so that we know that he's supposed to be yellow. Okay. So we got a nice Pikachu there. You don't have to draw. you really don't have to draw this on your paper, but I like to draw and I like Pokemon and I like physics. So I'm just gonna put all those things together. My art teacher told me one time when I was in college, I thought I was gonna be a comic book artist. He said, if you do what you love, you never have to work a day in your life. Okay. So if we had a video of that, we could see, all right, and let's draw Pikachu after he hits the wall. Okay, so Pikachu is in contact with the wall. So okay, here's Pikachu. We'll draw his tail kind of sticking out like this. Okay, and he is deformed somehow, and his head is kind of smushed out like. Don't worry, no actual Pikachus were harmed. I mean, not really. Okay, so Pikachu is squished together. Here's the red spots on his face. Okay. And he is in contact with the wall. Okay. Here's the smushed up Pikachu. Okay. He is making contact physically with that wall. Okay. And I think Pikachu, he's squishy. Right? He's a very, they're kind of squishy beings. Okay. So he's in contact with the wall for some time period. Okay. We'll call that Delta T. Right, this is the part where Pikachu is actually in contact with the wall. Now, he experiences some force, obviously, because he gets deformed. And so right here, we'll have the bottom axis be time in seconds, and this is going to be our force over here. Okay, so this is our force. Okay, so over time, initially as he makes contact with the wall, okay, then um, yeah, he's going to experience a certain amount of force here. Okay. And so we have this curve, right? The force goes up and then it goes down. Okay. Now, when we talk about the average force, okay, so this weird curve has, some area underneath it. Okay. We're gonna find that area, okay, underneath this curve. Okay. Now, if we talked about calculus, we'd say, oh, well, we can take an antiderivative of that. And if you're into calculus, I know a couple of you are, that's fine. But we're not going to talk about calculus. Okay? We don't want to talk about it. Okay? And here's why, because we don't need to talk about calculus, okay? Because we can just draw a box here. We'll say, all right, now I'm gonna draw a line here to the middle. I'm just going to the middle here. This kind of looks like grimace, but okay, whatever. I'm gonna draw a line here through the middle of this, and then I'm gonna make a box. Okay, I'm gonna start over here on the side where this thing starts right here, and it goes over to here where this thing ends. And then I'm just gonna go right in the middle here. I'm gonna cut it in half, and that's gonna be a box. And guess what? That is the area under this curve. It's the same area as this weird shape, okay? So. All right, we're gonna find that area here. Okay, so anyways, but this is our force curve. Here's our average force. Right, this is our average force. Not up here. That's actually wrong. It's this line right here. That's our average force right there in the middle. Okay. All right. Well, anyways, okay, going back to our Newton's law up here. Okay, so there's a couple things that we can do with this. First of all, I'm going to divide both sides by m here. I'm going to say divide by m. Divide by m. Okay. I promise you this has a point. Okay. All right. So now I've got acceleration on one side. All right. I've got my average acceleration here. And I say, well, that equals my average force divided by the mass. Okay. We haven't done anything too crazy, right? Yeah. We divided by m and our m's over here canceled. So we got acceleration on this side. Okay. And this is my average acceleration. Now, I can rewrite this. I can say, okay, here's my average force. Okay, this is divided by m. Okay, and I can also write average acceleration in a different way. Okay, I can say that this is actually equal to my average velocity divided by that time period. Okay, because right, um, right, we learned this before. Right, this isn't anything new or weird or kind of crazy, okay? Because we saw before at the beginning that average acceleration is equal to the change in velocity divided by time. This was from chapter 2 or 3, okay? So we haven't done anything weird. Not yet, anyways. We're about to do something, okay? So this is the same thing, right? We just wrote acceleration in a different way. That's fine. Nothing weird there is going on, okay? But now that we've separated these, okay, we can rearrange things. So I'm going to do a couple of things right now. First of all, I'm going to multiply both sides by m now. Okay? M was over here on this side. I moved it to this side, and now I'm moving it back. Okay? So my m's over here going to cancel. That's fine. Nothing weird yet. Okay? And now I'm going to multiply both sides by delta t, right? I'm going to multiply over here by delta t. I'm going to multiply over here by delta t. Okay? So my delta t's over here cancel. Those ones go away. Okay, so now I'm gonna rewrite everything that we have left here. So I'm just gonna say average force times delta t is equal to m times delta v. Okay, now over here, where's delta t? Well, let's say this bottom axis is time here. Okay, and so my the time is equal over here to delta t, right? That is delta t, right? From the bottom over here, the beginning of my collision to over here, that is delta t. Okay? And then F average here is this line. Okay? Well, um, yeah. So, um, I know what F average is. I can look at this and I can draw it, and I know what delta t is over here. And now I can just have m times delta v. Okay, and so this is another way I can write this is m times final velocity minus initial velocity, okay, is equal to F average over delta t. Okay? Hopefully you're with me. Okay, now this side is interesting over here because I could also rewrite this and I could say, well, this is actually just equal to final momentum minus initial momentum, right? Because I know that my final momentum is equal to mass times my final velocity, and my initial momentum is equal to m times FVI. Okay? So this is really important. This is the important point that I'm getting at here. We're almost there, okay? And then we're gonna do this problem, okay? So we started off trying to solve that problem. We threw Pikachu against the wall, not because we don't like Pikachu. I love Pikachu. It's my favorite Pokemon. Okay? And this side over here is equal to average force times delta T. Okay? Well, all right, now this is equal to delta P. We'll just call this change in momentum, okay, is equal to force times the average force times delta T, the time of the collision. Okay, now this idea here of the change in momentum, okay, this is a very special quantity, okay, and we're gonna introduce this concept of something called impulse. Okay, and okay, we're gonna call J. We're gonna say that J is impulse. Okay, J is equal to impulse, and J, okay, is also equal to delta P. Right? So impulse is equal to the change in momentum, and it is also equal to my average force during a collision times the time interval of my collision. Okay, and let's write down some terms here. Okay, so delta t, okay, is the time of collision. That's how long did the collision last? Okay, now we're going to talk about what this means. Okay. And F average, that's the average force. Okay, this is the average force experienced during collision. During collision. That's the average force during the collision. Okay? And delta P is the change in momentum. Change in momentum. It's the change in momentum during the collision. All right. Now, remember that and we'll call J here J. J is the impulse. Okay. Now, why do we care about this? Why do we care about impulse? Okay, and what the heck does impulse even mean? Okay, so impulse is a way to determine how much force you will experience in a collision. Okay, and this is very relevant if you drive a car. Okay, now I don't know if you've ever been in an accident before, but modern cars have a lot of safety features inside of them to uh, reduce the force that you experience during a collision. Okay, because that's really the key factor of are you going to survive a collision in a car accident? Okay, now a long time ago, the interior of cars were different. Okay, for one thing, you didn't have to wear seatbelts, right? And if you did have a seatbelt, at first it was just a lap belt, so it just went over your lap. Okay, and so imagine I'm driving along in my car, woof, driving, okay, and the car in front of me stops. It's like, oh shoot, oh, okay, that's what would happen. Okay, you would if you weren't wearing a seatbelt, you just continue flying forward. Okay, so if you're on a freeway and let's say your car comes to a stop, okay, you and the driver will continue forward. That means that if you're going fast enough, if your car stops, you will continue through the windshield. Yes. So just keep on going, right, in a straight line because you had a certain momentum and your momentum is conserved and it does not change. So you will be launched out of the car. People would go through the windshield. And of course, back then, before the 1940s, they didn't have um, tempered glass, meaning it was just glass like in a window. Okay, so if you hit the windshield and you were going, say, uh, 60 miles per hour or 30 meters per second, you would continue through that glass window at 30 meters per second, right? The window would break and it turns into basically a meat grinder and you are instantly killed. Well, if the windshield didn't kill you, being launched in the air at 30 meters per second definitely would. Okay. So, people eventually started putting seatbelts in cars because so many people were dying in car accidents. Like, if you got in a high-speed car accident on a freeway, you were dead, right? You were just dead. And, for a long time, people resisted wearing seatbelts. They're like, I ain't gonna wear another seatbelt. I'm a, I'm an American. I don't need to wear a seatbelt. Right? You're infringing on my liberty. People didn't want to wear seatbelts. Okay? And there was a lot of evidence um, that indicated that wearing a seatbelt can save your life. Okay? And the car industry fought it for years and years until eventually, people in Congress came together, Republicans and Democrats, and said, hey, we don't want people to die pointlessly. And so, yes, you should wear a seatbelt. Okay. Now, at first, seat belts just went over the lap, and so when you were driving, right? Imagine you're driving your car now in the 1950s, of course. Imagine the interior of your car, it's all metal. The steering wheel is either metal or wood, but it's not squishy at all. Okay? It's not squishy. So you're driving along, you have your seatbelt on, you're like, doo 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 doo. Oh no, the car stopped in front of me. Yeah, I love doing that because it's like it's like a dashboard cam, okay? Your head is gonna hit the dashboard, the steering wheel. It's made out of metal. There's no cushioning. Okay? Uh no airbags. Okay, so boom, your head just hits the steering wheel. Now, one time in my I don't want to say misbegotten youth, but again, I was in college and I was driving a car, and I didn't have my seatbelt on. I always wear my seatbelt now, but I made some poor life choices, perhaps. Not wearing a seatbelt is a poor life choice. And so I was driving along in my car, and I was only going 25 miles an hour. And somebody waved at me. They're like, "Oh, hey, David, how's it going?" And I was like, "Oh, hi, how's it going?" And I was driving a 1982 Chrysler station wagon. Solid steel, huge car, really massive. And in front of me, as I was waving, see, I was distracted driving. This was before cell phones were an issue, but um, so I was driving and I turned to the side. The car stopped in front of me. I was like, "Oh, hey, how's it going?" Car stopped. I hit the car. Oh. And of course, my head hit the windshield. I cracked the windshield with my head. There was a big star mark there. That was from my head. I guess fortunately, I have a pretty thick skull. So eventually, I was fine. I was a little bruised, but um, the time of the collision was very short. Okay, and so had I been wearing my seatbelt or had my car been newer, the airbag would have activated. Okay, which what it does is it increases the time of the collision. Okay, so now let's look at our equation here. Okay, so right here we have delta P, change in momentum equals the average force times the time of the collision. So, if we want to find the average force experienced during the collision, we divide both sides by delta t here. Okay? And so that gives us that delta p, okay, divided by delta t. Right, I'm just going to divide both sides there by delta t. So we'll have a divided by delta t divided by delta t. Okay, they're going to cancel here. Okay, and so I end up with my average force is equal to the change in momentum divided by the time. Okay, so the now if delta t is small, okay, my average force is going to go up. Okay, and let's look at an example here. Maybe let's you know what let's do some let's simulate Dr. Wisby's collision with the windshield. Okay. So let's put some numbers in here. Okay, let's calculate the my impulse as my head collided with the steering wheel. Let's yeah, let's put in some numbers here. Okay, so let's say that my at the time my mass we'll go with a mass of 80 kilograms. That's about a human mass. And my velocity, I was going 25 miles an hour. Okay, and so that's going to be a velocity of 12, we'll go with 12.5 meters per second. That seems reasonable. Okay. And delta T, okay. Well, my head bounced off the windshield, and so um we're gonna have to collect a little bit of data. I think probably let's go with you know what? I'm gonna get my little sensor out here. Yes, where did my sensor go? All right. We're gonna collect some data. We're gonna simulate Dr. Wisby's crash. Oh no, my EV sticker's coming off. Ugh. All right. All right, I think it's mostly okay. Give me a moment to boot up the sensor. Right. Now, I apologize if this video is a little bit longer. I hope somebody would watch it. I hope someone watches my videos, but I understand if you're just reading the chapter, like, I get it. That's fair. I understand. But, okay, so we plugged in the sensor. I need to go to the website. We're gonna do a little experiment here. I don't know what the collision time was, honestly. Right? And no, let's assume that my head is bone, but I think if we just bounces off of something sort of hard, maybe plastic, maybe hard plastic. Let's say that simulates my noggin. Okay, so let's go over here to our sensor. Okay. And we're gonna do a new page. We're gonna oh, we need to make sure our sensor is on. Activate sensor. Activating force sensor. Yes. Okay, so what do we got here? Are we reading anything? What's going on? I need to connect the dongle. There it is. Okay. Connect. All right. So it is connected. And here's our sensor. We need to calibrate the sensor. So I'm gonna calibrate. You need to put it this way. Calibrate. Calibrate force. Okay, put the sensor on its head. I'm gonna calibrate it. Okay, and then the mass of the remote is 2.2 kilograms. Lift the device. Okay, so I'm gonna hold it by this little metal thing here. Calibrate it. All right, save our calibration data. Save our data. All right, we did it. Then I'm gonna get my force here, okay? And let's do my accelerometer. We're gonna get force and acceleration. Yes. There's actually an accelerometer inside of here, but then there's a force sensor attached to this thing. Okay. So we'll do validate our configuration. Okay, so here's our accelerometer, and here's our force sensor. Okay. So I've got this plastic cup I keep my pens in here. I'm going to hold on to this really tightly, and then we are going to activate the sensor. Why isn't it activating? What does it say? Oh, what is this? No, I calibrated the sensor, man. What? Okay, we need to recalibrate. Where did my calibration data go? Okay, well, remote, calibrate, force. Oh wait, maybe it wants me to does it want me to calibrate the accelerometer? Oh jeez. All right, you know what? I'm not gonna do this. All right. We're gonna do a new page. We're just gonna do force. It's taking too long. Yeah, all right. Force. Validate your configuration. Ah, here we go. All right, here's my force. We're going to record, okay, the force during my collision. I don't know if I can get 12 meters per second, but we really just want to get the time of our collision. Okay, so this thing is going, and I'm gonna just ram it in here. Aha! We did it. Oh, what happened to our force sensor? Yeah, we'll do it again. Okay. No, I want it to bounce. All right, there we go. We got some data. All right, let's look at our average collision time there. I don't know what happened to my sensor. Why is it? Okay, whatever. Let's look at our what are we doing? All right. Yep. move this down. Here's our initial. So we can zoom in here, okay, and we can make our force curve. Aha! Okay, so the average time here, we're going to zoom in a little bit more. Okay, all right, here we go. So the bottom axis is the time here. I think right here, this is when we start and we go over to here. So we're going to say the time during the collision is 0.03 seconds. Okay, and this is going to give us, this is kind of cool actually. Okay, because we're going to calibrate, we're going to kind of come up with an estimate here of what kind of forces were experienced by Dr. Wisby during the collision with the windshield because he was not wearing his seatbelt. And then I think we're going to look at the force it takes to give you a concussion. We're going to compare those two things. Okay. So it looks like the time is 0.03 seconds, right? Because I go from right over here 9.80 to 9.83. Okay, so that's my time of the collision. Let's just see what force this gives us. I mean, right, we're doing a model here, and we took some simulation, right? We collected a little bit of data, right? We're basing this off of a real set of data here. Okay. So we actually collected some. Yeah, I'm gonna leave this page. All right. Now I'm gonna turn off my sensor. Save. Oh, it already turned off. All right. All right. Yeah. So, all right, we have a time now. Okay. And let's see. During the collision, I came to a stop. All right. Now that's really important. I didn't bounce. So, oh, wait a minute. This is actually kind of an inelastic collision. Ah, but my head bouncing off the windshield, that was an elastic collision. Yeah. So, how much force did Dr. Wisby get on his head when I bounced my head off of the dashboard? And I already simulated that, so I won't do it again. Okay. So what do we got here? Um, oh yeah, the mass of me. All right, so all right, here we're gonna plug in the numbers here. Okay, we've got yes, the mass of Wisby, Wisby's mass, m whiz times my velocity. That's the velocity of Wisby. Yes. Divided by the time that my head was in contact with the dashboard. Now, let's just assume, just for fun, that it was 0.03 seconds. Right? That's the time of the collision. Now, it is a little bit different because if you look at the end of my sensor, okay, it's metal and the cup was plastic. These are hard surfaces. Now, your head is not metal. There's, a little bit of skin on your bones, right? Maybe a little bit of subcutaneous fatty tissue. I think that's what you call it. Okay. I don't think I have that fat of a forehead. How fat is your forehead, Dr. Busby? I don't know. That seems wildly inappropriate, but you're all adults. Okay. So we're going to plug in the numbers here. So the mass of Wisby, we'll say 80 kilograms. And my velocity is 12.5 meters per second. And the time of the collision, oh, this is not looking good. 0.3 seconds. Okay, and this is going to be the average force that I experienced during this collision. Okay, and I have a bad feeling about this. Did I get a concussion? Hmm. No, I don't know. All right, well let's try this. All right, we're gonna put in the numbers here. So we got 80 kilograms. No, we don't want to use this. Times 12.5 meters per second divided by the time of the collision, 0.03. Oh, that's gonna be a lot of newtons. Oh, geez. Okay, that's 3,000. Okay, format long. Okay, let's do that again. Okay. That's I think is a little too high. Okay, so 3.33 times 10 to the 4. Okay, so that's 3,330 newtons. That's yeah, and there's newtons there. Okay, so that I don't think that can be right. Now, maybe that was the so three. No, that's 30,000 newtons. Okay, well, okay, that definitely isn't right. But uh force required for a concussion. Mm, that is, let's see. In adults, a concussion generally requires an impact of 70 to 100 Gs. How many? Okay, so this can't be right. All right, because if it is, if you want to find out a G, you divide by 9.81, or we'll just say 10. Okay, so that is 330 Gs. Hmm. Okay, that now this was just based off of this metal sensor, but that seems a little bit high. 333 Gs. Okay. Let's put in another question. Let's see if AI can help us. What is the collision time if your head hits the windshield of your car going 25 miles per hour? 100 milliseconds. Hmm. Okay, so that seems a little bit more reasonable. Maybe yeah, so maybe zero point 0.1 seconds. Let's throw that into MATLAB, and I think that's hopefully a little bit more reasonable. All right. So instead of 0.03 seconds, let's do 1, okay? Ooh, that's still 100 Gs, okay? Or 1.5. All right. So let's go with the time of so here if delta t equals 0.15 seconds. Okay, so that's the collision time with the windshield because the windshield did break a little bit, right? That it breaks, and so that increases the impact time. Okay, so in that case, the average force is going to be, according to what I calculated, 600 and 66 newtons, or we'll just call it 700 newtons. Okay, 700 newtons. And then if we divide that by 10, that gives us basically 70 Gs, right? So that's the F average. All right, so just looking at this, let's go back to our previous page. Oh, where? Let's go back here. Okay, so I would say the lower range then is 70 Gs. So uh, during my collision with the windshield, all right, I think that the average force that I experienced was probably around 700 newtons. That's on your skull. And this is only going 25 miles an hour, okay? So what I'm telling you is that 25 miles an hour, the average force that you're going to experience on your skull, if it hits the windshield, is enough to give you a concussion. You're going to experience upwards of 70 Gs, possibly 120 Gs, okay, which is definitely enough to get a concussion. Now, if you're going faster, right, the faster you're going, the higher that force that you're going to experience. Let's see what we're going to use AI a little bit here because I have no idea what the numbers are. All right, we'll go back to our query here and let's change let's say 60 miles or maybe 50 miles an hour, right? That doesn't seem that long. Okay, well it actually that part doesn't matter. Aha! But if we're going 50 miles an hour, that does. Okay, oh, so let's calculate this, okay? So here's my equation for um yeah, this is my equation for the average force that you would experience. Let's double our velocity from 25 miles an hour and let's do yeah, 25 meters per second. Okay? So, okay. If you double your initial velocity, okay, so if you're going 50 miles an hour instead of 25 miles an hour, it obviously doubles the force that you experience during that collision. Okay? If you let's say you're going 80 miles an hour, right? So now you're going oh well let's just double it again, right? So that was 50. Let's say you're going 80, so that's 40 meters per second. Okay. So that is going to be around 200 Gs. Okay. So what did we learn today? Okay. Okay. And um now yeah. So what did we learn from all this? Well, even if you're traveling at 25 miles an hour, if you're not wearing your seatbelt, okay, and you are in an accident, you can get a concussion even at 25 miles an hour. You could experience a force upwards of uh yeah, 700 newtons or 70 Gs. That's 70 times the force of gravity, okay? If you're going even faster, you're dead, okay? So at a certain point, that force is gonna your head is not as hard as the window, and so you will die. Thanks for watching this video. I will keep posting videos, and there will be. I will start. I am preparing the review for the exam, so there's going to be a practice test available. Thanks for watching.
Thank you. Like and subscribe down below.